it before it goes too far. There we go. Just hate reading what I'm saying in a transcription. Something about that disturbs me. All right, let's start. Okay, so last time we didn't exactly reach here. We got very close to the end of the last section. So if you guys want to continue with where we stopped the last time, I think we finished this example here with the 9 shirts and 5 pair of pants, all of this stuff.
Så ik weet ikke, fordi den område...
Sorry, I think someone's mic is unmuted. Okay. Anyway, as I was saying, I think we did this example the last time, and I think that was probably one of the last things we did. So there's not too much more left in that part of the section. I would recommend if you guys want to really get everything from the section, the next example is important, and it's quite straightforward as well. Well, once you know what to do, it's quite straightforward. So the detailed solution is in the module manual for this example. It's just simply drawing Venn diagrams and extracting information from it. So it's quite a helpful one. Okay, but for now, what I want to get to is counting and data representation, because there's a lot of stuff here. So let me try and get through the stuff which is difficult to learn by yourselves, and then the other theory stuff, if we don't cover it all, it's reading stuff, so you guys can do that. Okay. So again, somehow I'm a maths and physics person. I'm not sure why I'm teaching this section. I don't know why it's here, but for some reason I'm teaching it. I'm not an IT guy, so I'm just going to give you guys basic when it comes to the theory part here. Yeah, so the idea here is we're starting with data representation, and of course, computers basically process and communicate in binary, right? So here in the beginning, they want to give you guys some rough idea of what binary actually is in nature, because it has to be something that fundamentally comes from nature, and we have to be able to extract, something to give us two values. That's what binary is. As long as we can distinguish clearly between two different values, we have binary. And so usually, sorry, I'm just flipping my laptop over so I can write. I need to. Yeah, so usually these come in terms of things like the different poles of a magnet or different amounts of current in a wire. Usually we use wires with no current or wires with current to represent two distinct values, right? And again, very crudely speaking, of course, this is very crude now, guys, because I'm not an IT guy, but suppose you have something like a string of 8 wires. So I'll draw it like this: 1, 2, 3, 4, 5, 6, 7, 8, as a literal hardware piece in a computer somewhere, right? And this is connected to whatever, I don't know, some kind of decoder system. Okay, and in each wire we have different amounts of current. So we'll say either current or no current, right? So I'm going to represent I think I is what we use in physics in high school. So I will represent current. So suppose, again, very crudely speaking, suppose I press a key on a keyboard and somehow that key triggers a series of switches to switch current on and off in the wire, right? So suppose I press the A key, very crudely speaking, and what happens is that triggers a series of switches, which I'll represent here somehow. I think transistors are the more appropriate word, but anyway, switches, so we know what we're talking about. And that triggers current here, no current to the next one, current here, current here, current here, no current to the next one, let's say maybe current in the last one. Right? So the computer will recognize this as an input as places where there are current and no current. And we have given it the label. So a place with current, we will label it as 1. A place with no current, we label it as 0. So everything with current will be 1, everything without current will be 0. Right? So roughly speaking, this is how we get binary. Right? That's how we encode information, because when you press the A key, it will trigger a certain series of switches on and off. And then we decide that this series of switches being on and off, giving us the certain output, is the code for A. That's the binary representation for A, right? So that's where these things come from. I say in nature because current on or off is a natural process, right? Even though we are putting the switches on and off, we don't know how to make electricity. We just know how to sort of induce what's already there. We can create potentials and let electron flow and stuff like that, but that's a process that happens in nature already. We just enable it. So that's roughly speaking what binary is about. Now that we've gone through with that, which I'm sure someone else can explain much better to you guys, or you can read about it, let us get into the sort of the mathematical part of it. Right? So now we will talk about decimal, and from there we will get to binary because we know decimal already, we understand it. We probably don't think deeply about it because we are so used to counting in decimal, the usual way we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, so on, so on. We can do that with our eyes closed, so we don't think about it. But thinking about decimal helps us to understand binary. So how do we count in decimal, right? So once we hit, okay, again, I can't get into too much detail because of time restrictions, but roughly speaking, in decimal, once I hit 9, I must now induce a new digit, right? So if I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, once I hit 9, I can't go anywhere further, so I induce a new digit, which is a 1, and then my previous digit then goes back to 0, right? And with this new digit 1, it's a placeholder to tell me I'm in a different sort of level now, the tens here, right? Once we get there. So we do the same thing again, except now we keep this 1 constant in front of all of the digits. And then we just increment the first one. So I started from 0 here. I should have started from 0 there. We just increment the 0 again as we did before. 1, 2, 3, 5, 6, 7, 8, 9. And then we hit a 9 again, we have to do the same thing. The previous 1 now becomes a 2, and well, you guys get the picture, right? Everyone knows how to count. But just thinking about it this way will help us to understand binary. We reach the maximum limit of what we have available to us, which is a 9. Once we hit the 9, we have to now increment a new digit, right? And if we keep on going till we hit a 99, there's no place left to go, so we have to now increment a new digit, which will let it be 1, and we reset the other two to 0. Right? So this is how we count in binary. Now, counting in binary is not essential, but it can help get you guys some extra marks because there are going to be questions where they try to test your understanding. So it's good to know how to count in binary. So let's do it applying the same principle, right? Binary numbers only have 0 and 1. There's nothing else. So 1 is the maximum we can go to. So let's apply the same principle. Also, guys, now and then if you hear a baby screaming in the background, try to ignore it. Um, I'm doing what I can, right? Like with the door closed and stuff. Anyway, okay. So we start counting in binary, start from 0. Then we can go to 1 after that, just like before. But now uh, we can't go to 2 because there is no 2 in binary. So 1 is in inverted commas like our 9 here. It's the highest we can go to. So once you get there, you have to increment a new digit, just like we did before, and the old one goes back to 0. And then we start the process again. 0, 1. Now that, again, with that 1, we can't do much, so we have to take the new digit to 1 and increment the other one to 0. Right? And then the same thing again. Now we increment this to 1, 1, and this is like our 99 now. We reach it very quickly in binary because there's not many places to go here. So this then becomes 100. All right. So again, I can't really drill this into you guys' minds in this short amount of time, but hopefully you have enough of an idea to be curious enough to try this out once the lecture is done. Try to count in binary and see how far you can go with it. Okay, well, not see how far you can go infinitely long with it. Just try and get a few going so you have an idea. Okay, expanded form is another thing we've looked at before. I'm not going to get into that in too much detail. I'm just going to go straight into expanded form in binary. We know how to do in decimal. We've seen it before. So just this thing here, we've seen before, right? How to break a number 90328 into different components. And all they're showing us here is that what I just showed you above is the same as what I have down here, right? Representing with different powers of 2. I mean, sorry, different powers of 10. Right? I'm just going to give you guys a moment to look at this to see that these things are exactly the same. right? Because we're going to use this now to convert things from binary to decimal. And in fact, just get calculators going, sorry. Huh? Sorry. Just get a calculator going here. And you guys can, if you can please do the same, because I'm going to try and go a bit quickly with these. Okay. Old-fashioned calculators are a lot better than the apps because they take long to open. Okay, there we go. All right, so now this number from binary to decimal, we have a binary number right here. Convert to decimal, what we will do is just write this in expanded form, but using those instead of base 10, because we're binary now. Binary is base. So let's do it like this. I'll say 1, 0, 0, 1, 0, 1. Written in decimal is going to be, I'll start off like this, standard way. So just try and see what I'm doing here. I'm just going to repeat all the bits I see on the left. So the first one is a 1, right? And I'll write that times 2 and just leave it alone. This times 2 is something we will do for every one. I'm just going to leave it like that. So see what I mean? The first one was a 1, so I did that. The next one is a 0. So 0 times 2, right? The next one here is a 0. So I'll do the same thing, 0 times 2. Next one is a 1. So 1 times 2. And then we got a 0. So 0 times 2. And lastly, we have a 1. So 1 times 2. Right? Again, this may not make too much of sense, but I'm just trying to show you methodically how to remember what to do here. Okay, so all I did is times 2 for every different binary bit. Now, from the right going to the left, I start filling out powers of the 2. So the first 2 I will write as 2 to the 0. The next one I'll write as 2 to the 1. Then 2 squared, 2 cubed, 2 to the 4, 2 to the 5. Okay, at this point, we could just put this entire expression into the calculator and get an answer, and that will be our number converted from binary to decimal. So the answer will be the number in decimal, right? We could do that, or we could simplify it further by realizing that all these ones with a 0 in front, I shouldn't say ones, all these terms with a 0 in front, like this one here, contribute anything, right? Because 0 times anything is 0. So that's gone, that's gone, that's gone. It'll save us some time. And 1 times anything is just that thing itself, right? The 1 doesn't contribute anything. So from the first term, we will just get 2 to the 5. From this other term, we will just get 2 squared. And the last term, we just get 2 to the 0, right? So even though calculator work can be done here, it's not too difficult to simplify these things. Okay, 2 to the 5 is what? I think it's 32. Let me just check. Yes, it is 32. So this is 32 plus 4 plus 1, which is 32, 36, 37. Okay, so that's the answer. That's this number from binary to decimal. Okay. And soon we will start getting used to doing this in our head, right? Of course, it's good to start by writing an expanded form. Maybe for the first few practice rounds, you guys do that. And if you want to, you can stay there. That's okay. But if you want to try to get quicker, you can start taking shortcuts like going straight from here to here. Okay, but again, don't do that unless you're absolutely sure, because it doesn't get you any extra marks to skip steps, right? In fact, it's always dangerous to skip steps. Okay, now converting a number from decimal to binary, going the other direction is a little bit more tricky. Okay. Let me just check the chat in a moment because that was a complicated-ish thing that I did. Not too bad. If anyone's having trouble. No, I don't want to type. Thank you. Okay. All good. Please tell me the recording is started. Yeah, it is. Okay. Okay, so we're good. Okay, convert 70. So we're going the other way here. There are two methods to do this, and I'm going to show you the second one. The first one I learned is a little bit longer, but I'm more comfortable with that. But I've recently gone out of my comfort zone and learned the second one, even though I'm not an IT guy. So somehow it seems much quicker. So let's just do the second one. I'll be careful not to make mistakes. 75 from decimal to binary. Many of you would have seen this method before. I take the number divided by 2, and even though they're relatively easy numbers, I'm going to use a calculator. So I will get 37.5. Right? And now, apparently what we do here is we write this as 37, and if there's any remainder at all, right? So after dividing by 2, we get 37.5. So 0.5 is a remainder. It's not a whole number, right? So if we get any remainder at all, we write it as 37 remainder 1. As long as there's any remainder, we write the remainder to be 1. Okay, that's a weird thing, but that's what we do. All right, so now we and repeat the process. 37 divided by 2 gives us something which I'm not going to try in my head. Let's check this. 18.5. So same story here. We got some remainder, so we'll write this as 18 remainder 1. Okay, then we repeat it for 18. 18 divided by 2, that will give us 9. Clearly there's no remainder here. That's a whole number. It's a nice number. So we'll write this as 9 remainder 0 because there's no remainder. Okay, then we do this for the 9. 9 divided by 2 is 4,5. So this is 4 remainder 1. And I'll just keep on doing this. 4 divided by 2 is 2. There's no remainder here, so that's 2 remainder 0. Okay, and also it's important to know when to stop. I'll show you guys that in a moment. 2 divided by 2, it gives us 1. So that's 1 with no remainder. Okay, so now 1 divided by 2 gives us 0,5, which is 0 remainder 1. Is that right? Yeah. Okay, so firstly, how do we know when to stop? When this number here becomes a 0, that's when you stop. Okay. That's how you know when to stop. Now, this string of, well, not really a string, this it's like a column of binary numbers on the right. This thing is going to give us our answer. Read it from bottom to top. So the 0 comes first. I'll write that here. Sorry, that's a 1. I circled it. It's a 1. The 1 comes first, then the 0 here comes second, and so on. Just bottom to top. So 1, 0, 0, 1, 0, 1, 1. That should be the answer. Okay. So as an exercise, it's good to check these things. It's always good to check these things. And this we can check by repeating the step or repeating the above, because above we had something given in binary and said convert it to decimal, right? And that's relatively quick. So again, I showed you the long expanded form. I'm going to do this one using a shortcut method. If I confuse, excuse me, but it's probably good to see the shortcut method as well. So I will write it like this. Let me start from this side. The 1 on the extreme right represents a 2 to the 0. The 1 next to it represents a 2 to the 1. After that, there's a 0, so that doesn't count. That would have been 2 squared, but that doesn't count because there's a 0. Then after that, there's a 1 to the 3. 2 to the 4 doesn't exist. 2 to the 5 doesn't exist. 2 to the 6 exists. Okay. So what is 2 to the 6? I really don't know. I think it's 64. Let's just check it. Yeah, it is 64. Okay, so 2 to the 0 is 1 plus 2 plus 8, I think. Yeah, 8 plus 64. Does this give us 75? 64, 68, 69, 70, 72, 4. Yeah, perfect. Okay, so it works out. So this part here was just a check. This at the bottom here is not part of the thing, it's just a check. Okay. All right, no one said anything, so I assume I didn't lose anybody just yet, which is good. And this here, this is why I showed you guys the second method, because the first one is written here in the lecture notes. So you guys can read it and try this if you want to. Personally, I like this better. It feels a bit more intuitive, but it's slightly more complicated. Maybe I just like complicated things in my life. I don't know why. It'll explain a lot. Anyway, it's not a venting session. So we have some more examples. I'm going to do one of these because, let's see, should I? Are these important? I need to make a point somewhere here with something. Let's see if I can make it better later on. No, we need to do it here. So the point I want to make is sometimes you'll be asked something like, represent 101 with 7 bits. I'm going to call this part here with 7 bits. I'm going to call it, okay, let me not use weird Roman numeral. I'll say A. 7 bits represented with 8 bits. We'll call that B. And with 16 bits, we'll call that C. Okay, because it's a, okay, I don't want to waste time. Let's see. 101. What number did we just do? We did 75, right? So let me use the same number, 75, because we check how to do this again. Represent 75 with 7 bits, 8 bits, and 16 bits. I'm doing that because we just worked out 75, right? So I don't have to redo the whole thing. So 75, according to what we worked out up here, was 100, 101. Remember that? 100, 1011. Okay. So that comes straight out of our working. We don't really worry about how many bits are here. If I count them, it will be 1, 2, 3, 4, 5, 6, 7. So that works out to be 7 anyway. Okay, so let me take those bottom lines out if I can. Okay, so that works out to be 7. So essentially, A is done already. That is 7 bits. But now B, we need to represent this using 8 bits. So how I will do that is I'll just rewrite my answer 1001011, which is 7 bits. Now I need to include 8 bits. So naturally we want to include a 0 so we don't change the number, but the 0 must be on the left. So I will include it here because that doesn't change anything. If I include it in the front, it changes the order of magnitude. So I included 1 0 to the left to make this 8 bits. So we've done what the question asks. So that's okay. So naturally, C is going to be a similar process where I just write the original answer first, 1001011, and this asks for 16 bits. So what I have here are 7, right? 1, 2, 3, 4, 5, 6, 7. And you should just keep on including zeros until I get to 16. So we have 7 bits, that's 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, that's perfect. And you will find that if you check any of these answers, check the first one, check the second one, check the third one. When I say check, I mean convert it back to decimal. For all of these, you will get 75 back as an answer because I've put the zeros in such a place that it doesn't affect the number itself. Okay, so you guys can try the rest if you want to. Let's see what else we can do in this amount of time. A binary and hexadecimal. All right, so we know how to convert from binary to decimal and decimal to binary. Now hexadecimal is like a weird in-between space between binary and decimal. So we should probably start with an example. Let's see if they give us a nice one. Where can I do this though? Okay, I'll have to come back up here to make space. That's okay. So how can I copy this number? Okay, let me try and do this. So there's a big number here. I'll show you guys what to do. We'll learn with the example. 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 0, 1. Did I lose track here? I think I got it. So if these things should always start with 4, 12, 13, 16. Is it 16? Well, let me just see. Let me count them and see. 1, 2, 3, 4, 8, 12, 16. Okay, that's fine. So it must always have 16. If they ask you to convert something from binary to hexadecimal, you must start with a 16-digit long binary number. So that's what we have here, which is good. Okay, so the first step in converting to hexadecimal is to break this up into 4 bits each. So we'll break this up like this: 0101, 0011, 1001, 0001. Okay, same number, I've just spread them apart a little bit so we can see them in a better way. Now each bit of 4 needs to be converted into decimal. Okay, and again, we know how to do that. If we forget, we can go back and recap. That's okay. So maybe I should label these so I know which ones I'm talking about. I'll call this A, I'll call this B, call this C, and call this D. So convert A into decimal. I'll try and do this as quickly as I can without, if I lose anyone, they'll just stop me, right? We can recap if we need to. So 0101 in decimal will be, I'll start from the right. So this will be 2 to the 0 plus 2 to the 1 doesn't exist. And then 2 squared exists. 2 to the 3 doesn't exist. All the zeros, I'm going to just say they don't exist. So this is now 4 plus 1, which is 5. So that's the answer for A. That's A in decimal. Doing B very quickly, we'll have, I'll just write it in one go here. 2 to the 0 plus 2 to the 1. Everything else doesn't exist. 2 squared, 2 cubed doesn't exist. So this is just 2 plus 1, which is 3. So C is going to be 2 to the 0 plus 2 to the 1 is not there, 2 squared is not there, 2 cubed is there. So that's 8, 9. Okay. Finally, D is just 2 to the 0. There's nothing else there, all are 0. So that's just 1. Okay. So the answers to this put together represents the number in hexadecimal. So if I just write, I'll write it above by the question. That is equivalent to 5391. Just putting the numbers together, the answers. So that's the answer in hexadecimal. Now we must be very careful because this is not 5391. It's, again, it's a weird place between binary and decimal because it's representing each, it's a shortcut, it's a code for each string of 4 bits. All right, I hope you guys can see what I mean there.
In this case, we don't start writing the number from bottom up. We start up bottom. We go up bottom.
Oh, you mean right here, up to
Yeah.
bottom? Yeah, exactly. That's a good point. Thank you. Okay. Perfect. All right. It's good to hear something every now and then, so I know you guys are with me. So yeah, we just go in the sequence of what we've done. So we found A to be 5, we found B to be 3, and so on, 9, 1. So just it's in that order. Okay. So now suppose the number is slightly different. I guess we can make one up here to make the point. I'll make one up which is not too different from this, just different enough so I don't waste too much time, but I also show you what I want to show you. So this is the easy version of hexadecimal. One slight complication is if you had a number of the form, let's see, let me just think for a second. Let me make the number 1110. I'll already break it up, okay, just to save us some time. 1111, 1001, 011, 0. Okay, that one should work. All right, so again, we'll do it just as we did before. We'll label this A, B, C, and D. And now we just convert everything to decimal just as we did before. So for A, this will be 2 to the 0 doesn't exist, 2 to the 1 plus 2 squared plus 2 cubed, which just gives us 8, 9, 10, 11, 12, 13, 14. Okay, so this is where the problem comes in, because if you have something which is more than one digit, like in the previous question, we had 5, 3, 9, 1, all single digit numbers. Double digits cause a problem, and I think that should be evident because if you think about putting all double digits together, we'll get something maybe we'll see in a moment, right? So I'll show you guys in a moment. So b, let's work that out quickly. 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 to the 4 is 8, 9, 10, 11, 12, 13, 14, 15. Right? Makes sense because 15 is the biggest number you can make with 4 binary bits, and that has to be represented by all ones. 9,999 for binary. Okay, A, B, C gives us 2 to the 0 plus 1, 2, 3 plus 2 to the 3. That's 8, 9. Okay, which we've worked out before as 9, so that's fine. We verify that. So D is now 2 to the 0, doesn't exist. 2 to the 1 plus 2 squared, which is 4, 5, 6. Okay. So now you can imagine if I write this final answer, it will look like 14, 15, 9, 6. And that's not so nice because we can't distinguish whether our first number is 14, the second number is 15, or maybe the first number is 1, the second number is 4. You know, we can't really tell. So this is not good, right? So we have a little bit of encoding here. It's not difficult to remember. Anytime you go past, do we have a 9 somewhere? Yeah, sorry, this was supposed to be a 9, right? C is supposed to be a 9. That's not a plus, that's an equals to. So anytime we go over 9, if we get the number 10, we represent it by a letter. So 10 will be A, 11 will be B, 12 will be C, and so it goes all the way up until 15. Maybe we should just list them because we're pretty much there. 12, 13, 14, 15. A, B, C, D, E, F. Oh, okay, just barely fits. So using this coding, we can write our final answer using this. So 14 becomes E, 15 becomes F, and then you got 96. So that's it. That's much clearer to read. We can clearly see everything here represents a string of 4 bits. So we can undo it and work back to what the binary number should be. Okay. So that is hexadecimal. Those are the only 2 possible cases you will get for these things. All right. So now we're going to do some terrible things here. Convert the following to hexadecimal. Again, right, you guys can try that. Okay, actually, these two can't be converted to hexadecimal. They can just be converted to decimal because they're not 16. Okay, so you can try for 3 and 4. 1 and 2 you can practice converting just to decimal. Okay, representing negative numbers. Yeah, so we've done positive. Now we need to do negative numbers. So you'll notice every number we've worked with so far has been a positive number. We now need to represent negative numbers. Okay. And this example we can skip because it just makes the point of what I wanted to show you guys about how to represent a certain number with different numbers of bits. Right, 7, 8, and 16. We've done that already, so we can skip past that for now. Now we'll learn about this thing called a simple sign bit. It's a kind of outdated method that's not used anymore, but I guess for sort of historical reasons, we will learn how to use it. And we'll build upon this method for the next part, which is actually used today, which is called 2's complement. So we start with this thing called a simple sign bit to show how to represent a number or a negative number in binary. Okay, so the example given is if 59 is given by this here in binary, then if we're using a simple sign bit, it means that the first, okay, how many bits do we have here? 1, 2, 3, 4, 5, 6, 7, 8, right? So usually 8 bits is used. The first 7 here represents the actual number, or rather the magnitude of the number. I'll represent it in 2 lines here, magnitude of the number. And this last bit here represents the sign. So this magnitude part, which is just 0, 1, 1, 1, 0, 1, 1, if we were to convert that into decimal, we would find it should give us 59, right? Because that's the number part. So what does it actually give us? 2 to the 0 plus 2 to the 1 plus squared cubed 2 to the 4 plus 2 to the 5, right? Whatever, that should give us 59, okay? You guys can check it at some point. But the sign part, if the sign part is 0, it's positive. It's a positive number. If the sign part is 1, it's a negative number. So notice that the difference between what I just showed you and what's here is only the sign part. This is exactly the same as the previous one, which represents 59 magnitude. And this here has a 1, so it represents a negative number. All right, so it's the 1 which codes for a negative number. So that's using a simple sign bit. Okay, so using 8 bits as described above, what would the binary representation of these be? Okay, so let's do at least 1 or 2 of these. Okay, so let's see, where should we start? Let's start with this one here, -8. Let's try and represent that using a simple sign bit. So -8, the first thing we do is we just work out what is 8 in binary. That's the first thing. So what is 8 in binary? We will use the method I showed you, which is the easier method. So I'll start with 8, divide by 2. What does the method do? Divide by 2, you get an answer 4, and we check for remainders, right? So there's no remainder here. So I'll write this as 4, remainder 0. Keep doing the same thing with our answer. 4 divided by 2 gives us 2. That is no remainder, so 2, remainder 0. 2 divided by 2 gives us 1. That's 1 with no remainder. And finally, this should be the last one, I think. 1 divided by 2 is equal to 0,5. That's 0, remainder 1. And we can kind of see this is making sense already. So I'll start from here, 1, 0, 0, 0. All right, so that's 8 in binary. So did it say using a certain amount of bits? Yeah, it said using 8 bits. Okay. So this is 8 in binary using 8 bits. Okay, so that's going to be a confusing thing to write. So, okay, I'll write it like this. This is 8 in brackets using 8 bits. So using 8 bits, I'll just write the answer I worked out above, 1, 0, 0. But that's only 4 bits, so I've got to add zeros to the beginning to make it 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is my first, okay, rather my second step. First step was above to just find what 8 looks like in binary. Then we represent it using 8 bits. That's step 2. Step 3 is to now use a simple sign bit to represent this as a -8. So -8 using 8, be more specific, using 8 bits and using a simple sign bit. Okay, so that's the same as above, except now we add a 1 in front. 1, 0, 0, 0, 1, 0, 0, 0. Right, I specified using a simple sign bit because in papers and stuff, you will be told, are we using a simple sign bit or are we using 2's complement? 2's complement is the next thing we will learn. Okay. I really don't think I like that section, but we have to get to it anyway. Okay, converting binary with sign bit to decimal. Okay, so this just exercises you guys can try. Actually, is it? Yeah, maybe we should do a few of these because this is now kind of going the other way. Let's just do, let's see, I'll select 2 of them. Let's do the last 2. The last 2 always teach us the most stuff, usually. So what will the decimal values be for the following, assuming that the first bit is a sign bit? So that's what we will be usually told, right? You have to be told that the first bit is a sign bit. We can't assume it otherwise. Okay, so obviously this one here is going to just be some number which is given by this part here gives us the number. So whatever that number is, it's just it'll be represented by 1, 1, 1, 1, 1, 1, 1, which is 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2. How far do we go here? 0, 1, 2, 3, 4, 5, 6. So we go 6, really? 4, 5, 6. This is double check. 0, 1, 2, 3, 4, 5, 6. Yeah, okay, that makes sense because it's 7 bits and the 8th sign bit. Okay. So what number does that give us? I have no idea. I'm going to check in my calculator quickly. 2 to the 6 plus 2 to the 5. This, whatever it is going to be the biggest number that you can get. Okay, because everything's a 1 here. So I got 6, 5, 4, 3, 2, 1, and 0. That gives me 591. Is that right? Okay, but again, you guys can double check this. I don't want to waste too much time with the arithmetic because just if it's an error, it's a calculator error, or my error with the calculator, whatever. So the point is this bit of 7 numbers, this string of 7 bits represents this number 591. And that means that the number 0, 1, 1, 1, 1, 1, 1, 1 represents the same number, 591, because the 0 in front is a sign bit and it doesn't change anything. It's still a positive number. But this one at the bottom here is going to be negative because the sign bit is set to 1. So the last two are same in almost every way except for the sign bit. And we see the only difference is that the sign is changed. So done with that, let's see if we can get through 2's complement at least, because that should be the last heavy thing we need to do, I guess. Okay, so 2's complement is a bit more complicated because there are 3 steps here. 3 steps needed to be done to convert a number, to convert a negative number into binary using 2's complement. Okay, so let's just follow the steps and see what happens. I think there's an example here we can work out. Okay, why is it such a big number though? Can we do a smaller one maybe? So we don't confuse ourselves too much. We do a one that we already know the binary number for. Maybe we should do that. Let's do that. Let's look at one that we've done. Okay, not 591 because I'm not too sure of that. 10000. Okay, that's a simple one. That represents 8. So let's use that. So we know what 8 is. So just bear with me, guys. I'm changing this to just 8. So, okay, that's right here. Convert negative 8 to binary. Why is that word not here? Using 2's complement. Okay, so that we can do. So the first step says to ignore the sign, I guess. Convert the number to binary and don't worry about the sign essentially. So just convert 8 to binary, right? That we can do, that we've done. So step 1, 8 in binary is just 1000, right? But it's nice to use a consistent number of bits here, and 8 is usually a safe number, especially if you're dealing with smaller numbers like this. You'll usually be told how many to use, okay? If you're not told, you just use a standard like 8 or 16 or 32, but always use enough so that you have extra bits in the beginning. Like this ends on a 1, it's not good. We need extra bits so we can work with sign stuff. So let's just make it 8. 1000. So that's 4, 5, 6, 7, 8. Okay, so now we have 8 bits. So that's step 1 done. Convert the number to binary. Okay. 2 says invert all the digits, which means change zeros to ones and ones to zeros. So that we can do. Don't like when that happens. Let's correct that. Okay. So I'll change all the zeros to ones. So this becomes 1, 1, 1, 1, 0, 1, 1, 1. Okay, that looks a bit strange now, but that's step 2 done. Step 3 says add 1 to the result. Now this is where we need to be a bit careful. Adding 1 in binary, this is why it's useful to know how to count in binary. Okay, but anyway, this one here is a bit of a straightforward one. I'm going to just do it first, and then I'll show you guys. I'll try and work out a more intuitive way to do it. So I'll take 1, 1, 1, 1, 0, 1, 1, 1. And we need to add 1, but it must be a binary 1, right? We can't add a decimal 1. So adding the 1 must have the same number of bits as the number we're adding to. So that has 8 bits. So I'll write it like this: 1, 2, 3, 4, 5, 6, 7 zeros with a 1. That's a binary 1 with 8 bits. So if I add 1 to that, many of you will be able to see this. If you can't, it's okay though. This sometimes troubles me a bit as well. So adding 1 to that, it's as if this part here is a 900 why is it not happening? Is as if this part here is 999. So the next step after 1, it goes to 1,000. Right? So that becomes 1111, which is what we had before. That 0 becomes a 1, and the rest becomes zeros. Right? So that will take a bit of getting used to if you're not sure about that. Let me just see if that's the last. I'm sure that is the last thing to do. Yeah, that is the last thing to do. So this is the number in binary using 2's complement. Okay, but let me see if I can make a more intuitive way to add. Let's see if this works out. So I think if I just take the two numbers that I'm adding, 1110111, and add it the good old-fashioned way that we used to do in primary school, I'll say plus here. I'll write the second number at the bottom. Is that the right number of bits? 1, 2, 3, 4, 5, 6, 7. I think I lost one somewhere. Yeah, here and here. Let's double check that. 0, 1, 1, 1. Okay, that's fine. So everything's lined up. The plus sign is there. Now, so I'll start from the right. Starting from the right, I'm adding 1 and 1. Of course, we know that gives us 2, but in binary, 2 doesn't exist. So 1 and 1 is going to give us 10. Okay, so 10, I'll write 0, carry 1, and then we just keep going like this. This is 1 plus 1 plus 0, which is another 10. 10, carry 1. 1 plus 1 gives us 10 again. So 10, carry 1. 1 plus 0 is 1. And the rest are all just going to give us 1s. 1, 1, 1, 1. So that is the result. And that's exactly what we got on the right. So that's a relief. So it works out. Okay. And I think there's just an additional rule here. It wasn't needed in this case, but if you're doing something like this and somehow you end up with an extra 1 here, that happens sometimes. If you get a 10 in the end, then you just note that however many bits we were using in the beginning, which was 8, your final answer must also have 8. So you just sort of truncate it here. You get rid of whatever is extra, and the answer is just what's on this side. Just if that happens. Okay. All right, so that's that. So is this the same example? Okay, that's the one they gave us above, so you guys can try this as well. They give us the steps and the answer at the bottom. Okay, here they're adding a 1 like this without incorporating the right amount of bits. But anyway, we know how to correct that. I've shown you guys how to write a binary 1 with the right amount of bits, so that's okay. More examples that you guys can try. Okay. Converting 2's complement number back to decimal. I think this is the one that disturbs me a little bit. Let's see if we can get it. Okay, so we give an example here and we have steps to follow. Let's give it a try. Okay, so first thing we do is subtract 1 from the number. Okay, and I think that's the part that gets a bit tricky because subtracting 1 in binary, it's not as easy as just doing the subtraction method that I did. Maybe it is, but I don't think it really is. Here we have to use a bit of intuition. So let's see. Let's take this number and try to do all the steps. 111 number 111 00010. So subtract 1 from this. That involves you need to think about this in a certain way. You should think about what number do I add 1 to get what I have here. What number do I need to add 1 to get to this number? Right, so let's think about it. If I had the number 0, 0, 0, 0, 1. If I add 1 to this, I should get back to what I have. Right, plus, I'm pretty sure that will work. Yes, that will work. I can see it already in my head. It will work. 3, 4, 5, 6, 7. Are they all 7, 8 bits? 1, 2, 3, 4, 5, 6, 7, 8. So if I add 1 to that number, I will get back to what I started with. right? So in other words, if I subtract 1, I'll end up with this number here. So again, there's a bit of intuition that has to go into this. Or you have to get used to working with these things, right? Just think about the question, what number do I need to add 1 to get back to my starting number? That number will be the result of subtracting 1. All right, so that's this number right here. Yeah, I'm going to leave this whole thing up here because, again, I don't like this. It gets a bit confusing. But once we're done with step 1, the rest shouldn't be too bad. So I'm going to write the result of step 1 here as that number, 0, 0, 0, 0, 1. Okay, that's the result of taking the first original number and subtracting a binary 1 from it. Okay, and in a moment, we'll check if our shortcut method works here. Or if our other method. I don't think so, though, but we'll check. Okay. Subtract 1 and then invert all the digits that we can do. 0, 0, 0, 1, 1, 1, 1, 0. That's step 2. Step 3, convert the resulting binary number to decimal and add a minus sign in front of it is step 4. Add a minus sign in front of it. Isn't that only if the number is negative? Okay, we're assuming we started with a negative number. So convert the resulting binary number to decimal. Okay, but let's think now. Do we consider the first bit to be a sign bit here? Let me just think. We inverted all the digits. So the first bit must be a sign bit. Because even in 2's complement, although I didn't mention it before, I think we'll see it later, the first bit still acts as a sign bit in 2's complement. So if the first bit is a 1, it represents a negative number. If the first bit is a 0, it represents a positive number. Somehow that always works out. Okay, so anyway, let's convert this back into decimal. So to do that, we will get, again, we'll do this quickly, to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed. Is that right? Not 0, sorry. We don't start at 0 because the 0th digit doesn't exist, right? It's at a 0, so 1. We start at 2 to the 1, 2 squared, 2 cubed, 2 to the 4. Okay, I keep forgetting these things. I'm sure 2 to the 1 is fine, 2 squared is fine, 2 cubed is 8, 2 to the 4 is 16. Must be because we're going in order. So 16, that gives us 24 plus 20 plus 4 is 28, so it's 30. Okay, so that's step 3. Convert the number back into decimal and add a minus sign in front of it. So finally we get negative 30. So that's how you convert a 2's complement binary number back into decimal. Okay, and again, guys, one thing I would really recommend is when you're practicing with these, we now have the luxury of AI tools, ChatGPT and stuff. You don't have to practice in the dark anymore. You can try these examples, and to check your answer, just put the question into ChatGPT. It knows these things in detail. It will give you the right answer, step-by-step details of how to do them and stuff. So use them and check them. It's always a good thing to do. It's a new tool we have. It's a great resource. So make use of it. Oh, we have the answer. Oh, thank God, it's the right answer, negative 30. So we did the right thing. Okay. So no need for ChatGPT for this one, but for the ones I haven't done, try them and check. Okay. And there's more here to try. So try these and check with the AIs whether you've done the right thing. Okay. This is interesting. Let me quickly look at this table because I think this stuff comes out in multiple choice on occasion. So it's just asking us how many numbers can be represented using 2's complement. So it's showing us that we're kind of losing representation by using a certain bit to represent a sign. Okay, so let me take this from the top so I don't lose anybody. So using 8 bits, unassigned range just means if I'm representing only positive numbers, how many numbers can I represent using 8 bits, right? And you guys may remember from the last time. If you don't, it's okay. If I have binary, every bit has 2 possibilities, right? So if I have 8 bits, I'm going to write it like this. 1, 2, 3, 4, 5, 6, 7, 8. Just putting it as dashes because it could be anything. Each bit has the possibility to represent two things. So for the first bit, if I consider only the first bit, I have two possible representations. If I consider first bit and second bit, for every option in the first bit, the second bit has another 2. So we multiply those together. 2 times 2 gives us the number of possibilities you could represent using 2 bits. And that makes sense because it's a small one. We can intuitively see it. 4 is the answer there. And using 2 bits, I can represent 0, 0, 0, 1, 1, 0, 1, 1. Those are 4 different things. Right? Using 3 bits, I just get another 2 to lay on top of that. So that's 8 now, 8 possibilities. And that's going to be too much to list out. But if you listed that out, it's not unreasonable, not unreasonably large to check. So you can check that if you want. Okay, and so on, right? So this is going to be 2 multiplied by itself 8 times for 8 bits. That gives us 2 to the 8. And what is 2 to the 8? It's probably this number down here. Actually, it's close. It's 256. And that makes sense because what that tells us is we could represent 256 different things, right? Whatever they are, we could represent 256 different species of plants, different animals, different whatever. As long as it's 256 different things, 2 to the 8, 8 bits can be used to represent 256 different things. That's why they're telling us here if we represent numbers, it can represent the numbers 0 to 255 because those are 256 different things because 0 is a thing by itself and the rest will make 255. So that's why just remember 256 different things can be represented. And that's also true here. Although it looks confusing, it is true because 0 is a thing. Okay. And now using 2 to the 8 different, using 8 okay, sorry guys, give me 1 second. Yeah, sorry guys, just okay. So anyway, for the second one, using 16 bits, it's the same principle. I'm not going to do the whole thing again. 2 to the power 16 gives us, it should be this number here plus 1. Let's just check it quickly. So yeah, the number is 65536. Perfect. So exactly the same as before. This represents 65536 different things, which is what we have here. 0 to that number is 65536 different things. Okay. And I hope you guys can see what's on the right here for both of these is still the same amount of number of different things we can represent. Right, so look at the one at the top for 8 bits. 256 different possible things that can be represented. So negative 128 to 127, if you count how many different numbers are represented there, it is definitely 256 different things. Okay, and the same is true for the rest.
Why does
So
it go
you
from
guys
the
can-
negative? Sorry, why does it go from 128 to 127? Why wouldn't it go 127 to 128? Or
I
is it
think
just
because
so?
so because if you check how many these are, it is 256. So I'm not sure why they picked these endpoints. Maybe you could have picked negative 127 to positive 128. But yeah, same idea. I don't think there's a particular reason why they picked that one.
Okay.
Okay, thank you.
So isn't it they picked those values because it's 2 complements, so it's like showing the negative range.
Yeah, could be. I mean, honestly, you guys probably know more about this stuff than I do. So I would trust Jared. Jared is probably right. Okay. All right, guys. So I think I need to stop here because I'm already over time, but I'll leave it open for questions if you have any. Let me just see what was left. We covered all the important stuff, yeah. So all this other stuff here is stuff you can read by yourself. It's a lot of theory here. Okay, so that's good. We did the important stuff. I'm going to just stop the recording here.